Good morning, everyone. Welcome to the Sai Vidya Institute of Technology online video tutorials. Today, we will be discussing about the derivation of voltage and current equations for a microwave transmission line. The microwave and antennas module 1. This is part of module 1 for VTU syllabus, subject code 18EC63, 6th semester ECE department. See, derivations of voltage and current equations for a transmission line is a very important parameter because so many times we have seen in the VTU question paper, this question has been asked as in various parameter with approximately 8 to 10 marks, sometimes even 12 marks also, along with the solutions. So derivation of voltage and current equations of a transmission line plays a very important topic for examination point of view. So we will see how this happens. The voltage and current equations for a transmission line. So let us consider a transmission line uh, with certain parameters as seen in the video. We have a resistance, inductance, transconductance and capacitance. These are the components: inductive, resistance, transconductive, and conductance. We have inductance, resistance, transconductance, and then we have a capacitor here. This is the differential inductive component. This is the resistive differential component, and differential capacitive component, differential transconductive component. Now the voltage appear at this end. This is the input voltage, that is Vz, and we know the voltage at this point is Vz plus delta Z or dz. Now voltage happening across these two ends. This is the resistive component, inductive component. Now, if the current enters through this level, that is Iz, now the current which is leaving output is I of Z plus dz, because of your dz component which is involved in this. Now to have a calculation, the voltage and current drop across the components, we'll apply Kirchhoff's current law. And for this C and transconductance, we apply Kirchhoff's voltage law. For this is the line in impedance and line admittance, and this is applied for Kirchhoff voltage law and Kirchhoff current laws. Now we apply Kirchhoff's current law for the first loop. Now current of, that is I, that is current drop, that is Iz minus Iz plus del Z, that is this one, this current and this current. R and G. Now this R and G components, this KCL we are applying. Now this component, when we apply, so G del Z, voltage across this, Vz, is this one. Now across capacitance, we have C del Z, this component. Now voltage across this capacitance is del Vz by del T with respect to T. Now to calculate the voltage drop across the small element R and L, we apply Kirchhoff's voltage law. By applying Kirchhoff voltage law, that is KVL, we get Vz minus Vz plus del Z, which is equal to R, that is a resistive component, del Z, I of Z plus del Z plus inductive component, that is L del Z of Z plus del Z by your del T. These two equations we have identified for the voltage drop and current drops across this transmission line. By partial differentiation, we can able to write further equations, current Iz and Iz plus del Z. Now we have to do the partial differentiation of these equations. So when we do by partial differentiation, we can write here Iz minus Z plus del Z is equal to minus del I of Z by del Z. Similarly, for voltage equation, we can, by partial differentiation, we can write Vz minus V of Z plus del Z is equal to minus del V of Z by del Z. Now we are going to use this formula and substitute in the equations, in these two equations, and we'll try to simplify and calculate the further equations. Now del Iz by del Z is equal to minus of G del Z Vz plus C del Z del Vz by del T. And also we can write, this is from above equations, del V of Z, that is Vz del Z is equal to minus of R del Z I Z plus del Z plus L del Z into del Iz plus del Z by del T. Now here, now if we transform the equation in the other form, then the current is changing with respect to Z, and voltage is also changing with respect to Z. To simplify the equations, we consider current positions and voltage current positions. So we can rewrite the equations in this form. Now, in terms of del Iz dz minus is equal to minus G of del by del T. This is capacitance values are taken into in this, and we'll place other terms as it is. What we can write is, for voltage, same equation, del Z minus of R plus L d by dt into I. That is correct. These are the equations useful to solve equations. This is del by del t. These are all differential part with respect to time. So we can consider as j omega. Now when we put this value, del by del t is equal to j omega, where omega is a 2 pi f. So what happens is, so dv by del I by del minus of g plus j omega c into v. And also dv by dz is equal to minus of second order differential equation with respect to z. Now, if we do that, now then also we have to find out the solution of second order differential equation. So now let us consider equation A and B like this. Now, if I differentiate equation with respect to d by del z square, that is minus of r plus j omega l I di by dz. Now we know di by z dz value, the equation A. So I will replace di by z value in this equation. D square v by dz square is equal to minus of plus get cancel. So r plus j omega l, that whatever value of the thing g plus j omega c into v. Now this equation we have got here, which is nothing but your similar to a second order differential equation. This is, we can call it as equation C. So therefore we have equation C is similar to del square v by del z square is equal to gamma square v, where gamma is the propagation constant. Now this is the second order differential equation. When we compare with the gamma, so we get gamma square is equal to r plus j omega l into g plus j omega c. Now here the gamma represents the propagation constant. So therefore we can write from the equation, from above equations, we can write gamma is equal to square root of r plus j omega l into g plus j omega c. Because it is the propagation constant, we can see gamma square is equal to this value. So therefore we write r is equal, gamma is equal to this value. So where gamma is a propagation constant of a transmission line. Now in this value of gamma, we can write in the form of alpha plus j beta. So this is your real part and imaginary part. Now here this real part actually represents the attenuation constant, and whereas the beta represents the phase constant. In this propagation constant, we have two, real part and imaginary part. Real part attenuation constant, B is the phase constant. We can call this equation by D, gamma square V. Now if we try to have the solution of a second order differential equation, because this is also a very important aspect, we have to solve these equations. Solution of equation D. So sometimes in the exam they will ask you to derive this equation and also solve this equation. So when you try to solve this, now because of this equation we can write v is equal to v1 e to the power of gamma minus gamma z plus v2 e to the power of gamma z, which is nothing but your v1 e raised to minus alpha plus j beta into z, just replacing this value by alpha plus j beta, and plus v2 into e to the power of alpha plus j beta into z. Now here, if this equation in this portion, two components, one portion this one and this one. So now this component is the forward wave. It is in increasing the position. As z is getting increased, this signal is getting increased. So this is called as incident signal or forward wave or forward signal. As the signal is getting progressed further, as the z increases, so the we can call this whole term as the incident signal. Now here, in this case, now this term is is just opposite to the first wave. This is called as a reflected wave or the reflected signal. Signal. We have forward wave and reflected wave. Now, similarly, we can have solution for current equation. Now, this is for the voltage equations. So we can have similarly solution for current equations. So we know the current equation, which is represented by I is equal to I1 e to the power of minus gamma z plus I2 into e to the power of gamma z. So similarly, just for in this fashion, not to understand the characteristics, impedance values and all, so we'll have to get these equations of current, and here we can just compare with the equations with the current equation here, that is your I is equal to dv by dz into L dy. This equation, if I equate it to I, so dv by dz is equal to r plus minus of r plus j omega into I. So this also I equals, so you can send the term whole term that side. So I is equal to dv by dz into r plus j omega, so something like that. We can have that. Same thing I will put it here in this format. Uh, or you can use this equation, any equation you can try it out. Now I'll try to take this one. I is equal to